Scientists have definitely measured a whole bunch of half reactions, and there's a whole bunch of them out there, and we're going to see some of them. Problem set 5 has a list of some of these potentials on there, and what they've done is they've listed them all as reduction potentials, which means they're being reduced. All right. An oxidizing agent is the same as something being reduction. So they call these reduction tables or tables of reduction potentials, and that's because they're all listed as reductions. It's in your textbook. I definitely recommend using the one in problem set number 5 because that's the one we'll be using a lot. But you can see literally everything, all the ones that are known, and there's more than that are out there, but it's a pretty extensive list, which is kind of cool. One thing though, because they're all listed as reductions, some of them we're going to want to see as oxidations, because in an electrolytic cell, you must have one being reduced and one being oxidized. You must have a cathode and you must have an anode. So if you do need to reverse a half reaction, and you will, you want to change the sign of the cell potential, but not the magnitude of the E cell value. So as an example, zinc going to zinc 2 plus 2 electrons, that's written right now as an oxidation. And this would not be in the table of reduction potentials because we don't put oxidations in with the reductions. Go figure. Anyway, if you wanted to put it in the table of reductions, you'd have to flip this equation around. You'd have to make zinc 2 plus 2 electrons going to zinc metal. So if you do that, you flip reactants and products, you change the sign of E, but that's it. All right, so E naught becomes a negative 0.76 instead of positive 0.76. Everything else is the same. Now, you will see this one in the table because that's a reduction. A table of reduction potentials mean a whole bunch of things listed as reduction, and they're usually listed by their E cell value, so most positive to less positive, or the other way, something like that. But just realize you won't see zinc going to zinc 2 plus, but you will see zinc 2 plus going to zinc. And it's easy to translate. Just flip the sign of E, you're good to go. E naught tables are usually listed, like I said, as reductions, and so there's many negative E cell values. But that doesn't mean that E cell values that are negative are bad. It just means that probably they would prefer to be oxidized. So generally speaking, as a rule of thumb, the negative E naught values that you're going to see, those things want to be oxidized, like zinc. On the other hand, the thing that have positive E naught values, they generally like to be reduced. And again, there's different variants, and we'll talk about that more, but that's kind of a rough rule of thumb. Negative E imply great oxidizers or reducing agents, and positive E values represent good things that like to be reduced or great oxidizing agents. So this is how people think about these. It's a little bit weird, but again, if you break all this down, you've got it. Just break it down into pieces that make sense. Here's the table of reduction potentials that we'll use in Chem 223. And you can find longer lists and all kinds of lists if you look online. However, the values we use and stuff will come from this table, so it's a good idea to check it out. Now, first of all of these are reductions. An electron is a reactant for all of these, okay? None of these are listed as oxidations. The second thing, this one is listed from most positive cell potentials to most negative cell potentials. So what that means is, we talked about them, the things that have positive E cell values are great things to be reduced. So for example, we've seen so many times that, for example, fluorine really likes to be fluoride in ionic compounds. Fluorine always likes electrons, most electronegative, blah, blah, blah. This has a really high cell potential. It wants to be reduced. On the other hand, down here on the bottom, you have things like lithium ions making lithium with very negative cell potentials. Well, the group 1A metals don't like to be pure metals. They would prefer to be cations. So if you flip the lithium reaction around, you get a positive 3.05 volts. That just says that lithium loves to be lithium plus an electron. It doesn't really like having lithium plus an electron making lithium metal. It's much more difficult. As you go up the list, all right, you can think about it that the things are more likely to be reduced, like fluorine likes to gain electrons. Things that are reduced are also, of course, known as oxidizing agents. On the other hand, don't think that the negative things are bad by any means. Negative things are just most likely they want to be oxidized. Lithium wants to lose an electron to make lithium plus, and magnesium wants to lose 2 electrons to make magnesium plus, etc., etc. And if something is oxidized, that also means that it's a good reducing agent. So these tables are really cool. Right in the middle, in this one, it's in a kind of a blue color, hard to see maybe. That's the She electrode. You can find this same table in problem set 5, and I do recommend you check it out. In electrochemistry, sometimes they talk about the northwest-southeast rule. And this is one way to tell if you can have a reaction occur or not. Now, northwest is upper left, southeast is lower right. And the rule here is that if you have a table of reduction potentials that starts positive and goes more negative, then any substance on the right will reduce any substance on the left. All right. So what that means, as we've seen, is that zinc can make copper 2 plus go to copper metal and zinc 2 plus if you flip the reaction around. The southeast part is the anode and the northwest corner is the cathode. All right. And so if you have a table in getting more negative cell potentials, then the northwest southeast rule is right. So you could say, for example, zinc would also do the same thing with H plus, but you wouldn't say, for example, zinc 2 plus and hydrogen. That would be the opposite direction. Now, I'll be honest, I don't really like the northwest-southeast rule. To me, that seems very arbitrary. You have to have a redox potential table that's listed in decreasing cell potentials, and honestly, there's some other types of tables out there. So I personally am not a big fan of northwest southeast, but some people really do, and I want to introduce it. My way of figuring out what a cell potential is just to literally take the reduction potentials. You'll have to rewrite one of them for an oxidation, which means you flip the sign, and then you just add the cell potentials. So this is more like a Hess's law, I guess, kind of way, but honestly, to me, this seems really easy. So let's say you wanted to find the cell potential for this reaction, which is 2 aluminums and 3 nickel 2 pluses, making 2 aluminum 3 pluses and 3 nickel metals. All right. So you'd go to a table of reduction potentials, and because they're listed as reductions, all right, they'll be listed like this. Now, notice that the nickel 2 plus is a reactant right here, and we want nickel 2 plus as a reactant. However, we really want aluminum as a reactant, and as a reduction, you can see that aluminum is listed as a product. So from the redox tables, we will keep the nickel as is, but we do need to flip the aluminum around. We want aluminum as a reactant, not a product. We want aluminum 3 plus as a product, not a reactant. So if you flip that one around, negative 1.66 becomes positive 1.66. You can add the aluminum to the nickel one. I started up there earlier, 1.66 minus 0.25, this cell potential 1.41 volts. Again, I call this Michael's method because I'm arrogant, I suppose. You don't have to do that by any means. I find this easier. Just remember, if you flip a reaction, change the sign, add them together, you're good to go. It doesn't depend on the number of electrons transferred. We'll talk about later a situation where it could, but not here. Let's say you wanted to find the cell potential for the reaction between copper and silver plus ions. And if you look at a table of reductions, these are the two values you get. And you can see copper is in the southeast and silver plus is in the northwest. All right. Well, there's 2 ways to do this. So here's the 2 half reactions. Okay. And the silver is okay as is, all right? Silver plus, we want it to go to silver. But copper 2 plus, all right, we want to flip that reaction around because we want copper to react with silver plus, not copper 2 plus with silver plus. So if you change that, the positive 0.337 volts becomes a negative 0.337 volts, and the overall potential here would be 0.80 minus 0.337, cell potential positive 0.46 volts. So this reaction, copper plus 2 silver plus, makes 2 silver plus copper 2 plus, positive 0.46 volts. So again, I find that very easy to do. Of course, you could also go northwest minus southeast, but I find that very confusing. That would be another way to do it. Any way you do it, just pick one method and stick with it. Don't try and flip it around. Again, I highly recommend that you just write out the half reactions, get them the way you want it. We wanted silver plus, but we wanted copper, not copper 2 plus, so we flipped that one around, change the sign, good to go. So this leads to the kind of question like this one. We've got a cadmium cell and we have an iron cell. And the question is, which direction are we going to go? One possibility is that cadmium would be oxidized to cadmium 2 plus and the iron 2 plus would be reduced to iron. But the other possibility, which at this point is just as likely, cadmium 2 plus could be reduced to cadmium metal, and iron could be oxidized to iron 2 plus. So which one is it? It's either going to be the top one or the bottom one. And the way to figure this out is to look at those tables of redox potential. If you look at the tables, iron plus 2 going to iron is negative 0.40 volts, and cadmium 2 plus going to cadmium is negative 0.44 volts. We're going to see here in a little bit that reactions are spontaneous, which means they happen by themselves when E values are positive. So what we want to do is we want to combine those two reactions in order to give an overall positive value. Now you must have something oxidized and something reduced, and right now they're both reductions. So we need to flip one around. Well, if you flipped around the iron one, you'd end up with a positive 0.40 volts, and if you add that to negative 0.44 volts, you're still going to get a negative E naught value. So you don't want to flip that one. You want to flip the cadmium one around, because if you flip the cadmium, your negative 0.44 becomes a positive 0.44, and positive 0.44 minus 0.4, you get positive 0.04 volts left over. So what that means is that in this reaction, the iron 2 plus is being reduced to iron, and the cadmium is being oxidized to cadmium 2 plus. There's other things you can do with cell potential. Maybe you're curious, can the iodide ion reduce water? I have no idea. No, seriously, as a human being, I know sometimes when people are backpacking or places with water that's kind of uncertain quality, sometimes you can use iodide to purify water. So, I mean, I don't think that iodide could be added to water and have a chemical reaction occur. It's supposed to purify the water. But that being said, I honestly don't know. So what you could do as a scientist at this point is you could look up in tables and you could find a water going to hydrogen and hydroxide, which is a reduction. All right, water here is gaining electrons to make those other things. And you could also look up the iodide ion going to iodine. It has a negative 0.535 volts. Well, this is first one was a reduction. The second one is an oxidation. So when you add the half reactions, the electrons cancel. You're left with 2 iodides plus 2 waters, making iodine plus 2 hydroxides plus hydrogen gas. That's great. What's the cell potential? Well, the cell potential as written, negative 1.363 volts. Now, negative cell potentials are not spontaneous. So here we would say that negative E naught not means that reaction is not going to happen. In fact, it's more likely to occur in the opposite direction, i.e. iodine reacting with hydroxide and H2 gas to make iodide and water. That would have a positive E cell value. But water, iodide ion reducing water, that's not going to happen, at least not spontaneously. And that's what that signs will help you with. Positive signs happen spontaneously, negative signs do not. The question here, will liquid mercury reduce tin2 plus to tin? Okay. In a reaction like this, and it says yes, no, or more information, all right, you have to be very careful where your reactants and products are. And what this is saying is that you want mercury as a liquid as a reactant because it's going to reduce tin2 plus, the other reactant. So if you look at the half potentials, well, tin2 plus is a reactant, so we don't have to do anything with that value. But you can see here that you want mercury as a liquid to react with tin2 plus. And mercury as a liquid is a product. We need to flip that half reaction around. And if you do, that's positive 0.79 volts becomes negative 0.79 volts. And if you add that to the already negative 0.14 volts, you're going to get some negative number, negative 0.93 volts. Negative cell potentials are not spontaneous. So when it says, will it reduce it? No. Non-spontaneous means, don't think so. You're going to have to do something else if you want your tin2 plus to turn into tin metal. This question says, okay, iodide won't reduce water. I understand. Can we make it reduce water? Ooh, well, negative 1.363 volts would really represent an electrolytic cell, electrolysis, which is when if you put the pieces together, nothing happens. However, if we add some energy, you can force these reactions to occur using external voltage. So the negative 1.363 volts, besides telling us that it's non-spontaneous, you can actually realize that if you were to add 1.363 volts to it, you could make this happen. And that's where external voltage comes in. And you can use voltage from an outlet in your house. You can use all kinds of, any way that creates electricity, like a dam or wind power or whatever and stuff. Any way you can get voltage, if you add 1.363 volts to it, you can make this happen. Batteries are great. Voltaic cells are great. Wind power, if you got a big windmill, whatever you're using for making voltage, you can do it if you add the positive version of that volts to it. And that's kind of a cool thing. So this is an example of an electrolytic cell. You have to add energy to make this happen. If you put iodide with water, nothing happens. But you add 1.363 volts to it, then you start having something happening. This is electrolysis. Electrolysis is really the act of adding electromotive force or voltage to a reaction to make something non-spontaneous happen. And that's pretty cool because normally non-spontaneous things can be tough to get them to go. In this case, if you just add some external voltage, you're good to go. The question sometimes pops up, are you cheating the second law of thermodynamics, like the delta S of the universe has to be greater than zero? And it may feel that way. Like it may feel like non-spontaneous reactions all of a sudden occurring would be that way. But what we're doing is we're really using second law to make the voltage in another location somehow, all right? We're using a battery, using up the battery or something like that. So that is where the second law is being appeased, and we use that energy then to make this kind of thing happens. So we're not really cheating the second law. It kind of feels that way, but you're not really cheating it. Darn it.